Hello and welcome back. This is Chapter 5, Video 6, in which we'll be covering the basics of overlapping quantifiers. For this video, we'll be using this nice simple interpretation over here. We've got a universe of discourse, including all people, living and dead. We've got two two-place predicates, and we're going to just need two names for this interpretation. Now up to this point, we've seen symbolizations with no quantifiers, symbolizations with single quantifiers, even symbolizations with multiple quantifiers, but we haven't seen symbolizations where the scopes of the multiple quantifiers overlap. That is to say, if you pay attention to this last symbolization, you can see that the main operator is this conjunction here, and the scope of the universal only extends over LXK. The scope of the existential extends only over LYF. The scopes of those two quantifiers don't overlap. It's the case of overlapping scopes with quantifiers that we're going to look at now. So if we start again with the simple Fred loves Kate, we just have the L predicate, F for Fred in the first position, and K for Kate in the second position. That's simple enough. And if we want to do something like this, someone loves Kate, it's easy enough to replace the F in the first position with an existentially quantified variable. As you can see, we get there's at least one X such that X loves Kate, or someone loves Kate. We could replace from the top sentence Kate with an existentially quantified variable and say that Fred loves someone. In that case, and I'm going to use a Y here for a reason you'll see in a second, we would have some Y, LFY. There's at least one Y such that Fred loves them. Fred loves someone. Now, a simple case of overlapping quantifiers is the combination of two existentials, where we could say someone loves someone. There is some X, there is some Y, such that LXY. So there's at least one X such that there is at least one Y, such that X loves that Y. Or we can think of this as saying is there's at least one pair XY, such that the first loves the second. We can do something similar with the universal quantifier as well. So everyone loves everyone would look like this. For all X, it is the case that for all Y, X loves Y. Now, a couple notes here. When we're using two quantifiers like this, what's happening is that the second quantifier is within the scope of the first quantifier. That is to say, if we look at the second quantifier here, its scope extends to the subformula immediately to the right. If we look at the first leftmost quantifier here, the same principle applies. Its scope applies to the immediate subformula to the right. And so the existential Y quantifier is actually within the scope of the existential X quantifier. Note that it would be a mistake to try to use the same variable in both those quantifiers. When scopes don't overlap, it's okay to reuse a variable, say X, a second time. But when scopes overlap, we cannot make that mistake of using the same variable over, because it won't be clear in the remaining formula which quantifier is relating back to that variable. So whenever we have overlapping scopes, as here, we need different variables. Note the same thing is happening here. We've got the universal Y with scope over this whole subformula, and the universal X has scope over that. And again, we have to use different variables here. It doesn't have to be the case that the X is the leftmost one or anything like that. That just happened to be the way I did it. Now, a question you might be asking yourself is, does the order of the quantifiers matter? Well, let's take a look here. We've got someone loves someone, and we've got some X is such that there is some Y such that X loves Y. We could also symbolize someone loves someone in this way. There is some Y such that there is some X such that x loves y. In this case, we get there's at least one pair yx where the second loves the first. Or we could do this. Keep the quantifier order the same as in the one immediately above, but change the order of the variables in the predicate. We get there is at least one y such that there is at least one x where y loves x, the first loves the second. And the fourth possible combination would look like this. Same quantifier order as the very first one, but with the variable order in the predicate as the one immediately above. Here we have there's at least one x such that there's at least one y, such that the y, the second one, loves the first. Now these turn out to be quantificationally equivalent. All four of them are equivalent. I'm not going to dwell on that discussion here. There's a nice discussion of it in the text. The key point is that when we're not mixing universal and existential quantifiers, the quantifier order doesn't matter. That means that over here on the right-hand side, everyone loves everyone. We can change around the quantifiers and variable order in the predicate as we wish, and still get everyone loves everyone. So it's also the case with two universal quantifiers that the order doesn't matter. All four of the symbolizations on the right-hand side there are appropriate for everyone loves everyone, and they're all equivalent. So we've seen what happens when we have overlapping quantifiers of the same type, two existentials or two universals. What happens when we have overlapping quantifiers of different type? Well, this is where things get interesting, and the story is much more complex. For this set of examples, I'm going to keep the x with the universal quantifier and the y with the existential quantifier, just so it's easy to identify when we're changing quantifier order or order of the variables in the predicate. First, take this sentence. This should be relatively straightforward. In fact, we can more or less read it off the English. We need, for all x, there is some y such that x loves y. For every x, there is some y that x loves. Everyone loves someone. Next, suppose we want to say everyone is loved by someone. Everyone is loved by someone can be translated like this. For every x, there is some y where that y loves the x. Everyone x is such that there is some y that loves them. Everyone is loved by someone. Notice that these two sentences mean two different things. It could easily be the case that we have a true sentence here. Everyone has some particular person that they love, while it be false that everyone is loved by someone. There might be some unloved people, even though those people would be loving. And the reverse could be true as well. We could have it be the case that everyone is loved by someone, but that there be some people, even though they are loved, do not themselves love someone, and so we could have true on the bottom and false on the top. So these clearly are not equivalent, and there's no implication between these pairs. Consider this example next. Someone loves everyone. First, notice that in contrast to the upper left, everyone loves someone, someone loves everyone should start with an existential quantifier. There is at least one y such that for all x, y loves all those x's. And for the fourth example, we have someone is loved by everyone. Again, we'll start with an existential. There is at least one y such that for every x, all those x's love that at least one y. Someone is loved by everyone. So a couple of points here. First, notice that these two on the right-hand side are not equivalent. We could have the top one be true. There's one person who's just so loving they love everybody, including themselves, while it still be false that there's one person that everybody loves. And vice versa. It could be false that there's one person that loves everybody, one super loving person, while it be true that there's one person that everybody loves. So they're not equivalent, and there's no implication relation between them. But what about from corner to corner, diagonally? Suppose it's true that someone is loved by everyone. What about everyone loves someone? Well, that would have to be true as well, right? If there's one person that we all love, then we're all loving at least one person, namely that lucky, very loved person. So we do have an implication from the lower right to the upper left. What about the other direction, from the upper left to the lower right? Could it be true that everyone has at least one person that they love, while it is false that some one person is loved by everyone? Well, yes, that easily could be the case, so there is no implication in that direction. Because remember, the way these quantifiers function with the predicate variables is like this. What this says is for everybody in the universe of discourse, we must find at least one person that they love. So Fred could love Kate, Kate could love Sally, Sally could love John. As long as each person in the universe of discourse loves some particular person, the upper left sentence will be true. Down here, what's being required is that there is at least one person, and let's just focus on a single person. There's at least one person, say Kate, such that every person loves her. There's one unique, super loved person. And so we can have the top case be true. Everybody has somebody that they love, without it being the case that there's one person everyone loves. So we do not get the implication in the upper left to lower right direction. Now what about the other two corners? See if you can figure out or guess which way the implication is going to go here. Suppose first that it's true that some one person loves everyone. They're a super loving person. Then it will have to be the case that everyone is loved by someone, if only that one super loving person. So if the upper right is true, the lower left must be true as well. What about the other direction? Supposing it's true that everyone is loved by someone, must it be the case that some one person loves everyone? Well, no, it doesn't have to be. This could be false. And for the same reason we saw in the previous example going from the upper left to the lower right, let's look carefully at it. What the lower left one requires is that for every person, there be a Y that loves them. So maybe my mother loves me, your mother loves you. Everybody has some one person or other who's loving them. What's required up here is that there be one particular person who loves everyone, some sort of saint or something. And it's entirely possible for this to be true. We each have someone who loves us, while this, there's one person who loves everyone, to be false. So we don't get the implication from lower left to upper right. So this helps to illustrate the importance of the order of two different quantifiers, existential mixed with universal, and the change in the order in which the variables appear in the predicate. One last note on these simple examples. If you look carefully, you see that the quantifier order basically mimics the order in the English. On the left-hand side, we have everyone first, universal first, someone second, existential second. Then when we have the predicate in the active voice, the variable that's connected to the universal is in first position. The variable that's connected to the existential is in second position. But when we have the passive voice, we have the first quantifier moving into the second position and the second quantifier moving into the first position. And the pattern is the same here. We can read quantifiers pretty clearly off of the English. And when we have active voice, the order of the variables in the predicate is the same as in the quantifiers, first into first, second into second. But then when we have the passive voice, we have first quantified variable into second position, second quantified variable into first position. In more complex cases of overlapping scope, it's not going to be as obvious how to read off the English, but here it is. One last illustration of this example. Here we have the same four formulas and sentences as before, and next to each one of them over here we have a little illustration that shows a model, a situation that makes the corresponding sentence true. For example, 1 says that everyone loves someone. This was the upper left in the previous discussion. Well, if we look over at this model here, we can see that in fact everyone is loving someone. A loves B, D loves B, B loves D, and C loves A. So everyone has an arrow coming out of them towards someone else. And here we're imagining that the universe of discourse is just A, B, C, and D. And there are no other people. So each of these little guys has an arrow coming out of him or her because each of them loves someone. Similarly, if we look at 2, which was the lower left-hand corner in the previous discussion, we've got everyone is loved by someone. So B is being loved by A is being loved by B, D is being loved by B, and C loves him or herself. So now everyone has an arrow coming into them, meaning that someone is loving them. So we make the formula true. Notice, however, that the model for 2 does not make 1 true. The model for 2 makes 1 false. And the model for 1 makes 2 false. So we can see that there's no implication relationship between 1 and 2 there. Now look at 3. Someone loves everyone. If we look at C here, C loves him or herself, but also loves A, B, and D. So there is at least one person, this very loving C, who loves everyone. And so that picture makes 3 true. Take a look at 4. Someone is loved by everyone. Well, here C is the at least one person who's getting loved by everyone. Has arrows coming from everyone into him or herself. Very well loved C. Notice that the picture for 4 makes 3 false. In 4, there's no one person that loves everyone. There's no one who has all arrows coming out of him or herself to everyone else. Also notice that the model for 3 makes 4 false. In the model for 3, there's no one person who's getting loved by everyone. So there's no implication relationship between 3 and 4. This is just as we saw in the previous discussion, only now we have little pictures to visualize it. It is worth noting, however, that 4 implies 1. Take this picture for 4, which makes 4 true. It does, in fact, imply 1. 1 says everyone loves someone. And in fact, if you look down here, we've got B loving C, D loving C, A loving C, and C loving C. So everyone loves someone. It just happens to be, in this case, they're all loving the same person, unlike the above. Notice in contrast, of course, that the model for 1 makes 4 false. So there's no reverse implication from 1 to 4. So what we've just established is 4 entails 1. Similarly, take a look at the model for 3. This will make 2 true, so we do have an implication from 3 to 2. Everyone is loved by someone in this picture here because, in fact, there's one person doing all that loving. Whereas if we take this picture, everyone is loved by someone, it actually makes this false because there's no one person that's loving everybody. So we've established again that 3 entails 2, and those are the only entailment relationships here. Now, it's not that 1 and 2 are inconsistent. They can both be true, but there's no equivalence or implication relation between them. Similarly for 3 and 4. 3 and 4 can both be true, but there is no implication or equivalence relation between them. Each of the models here was chosen to demonstrate that except for these implications, these statements are independent of one another. As we deal with more and more complex formulas, where the quantifiers have overlapping scope, things get more and more complex. These basics will help you to learn how to apply these principles.